This is Suvarshila working as an associate professor in the Institute of Aeronautical Engineering. As a series of database management system lectures, today I'll explain various operators of relational algebra, two basic operators of relational algebra, which is a language used to query our database actually. The last session I explained relational database languages. Those are pure and categorized as a pure and commercial. That is, pure are mathematical based languages, commercial are the database languages which are used to implement our database on system. Similarly, another kind of categorization also we discussed, procedural and non-procedural. So as a part of that, the language, each language may have combination of these characteristics. Procedural pure languages, non-procedural pure languages, and procedural commercial languages, non-procedural commercial languages. This relational algebra is a pure language. This relational algebra is a pure language, and this is also a commercial language. So these two are the basic characteristics of our relational algebra. The relational algebra is used to query our relational database actually. These relational algebraic queries are written in relational algebra by using operators and operands. I already explained to you the basic operands used in our relational algebraic queries are relations only. Inputs are also relations as well as outputs are also relations. So what are the operators? Basically, the operators used in this relational algebraic queries are categorized into three categories. Basic relational algebra operators, derived relational algebra operators, and extended relational algebra operators. That means here, initially the relational algebra was introduced with the base operators, basic operators, but which are not sufficient to express our queries more effectively. So that's why by using these basic operations, to reduce our complexity of the queries, new set of operators were introduced, but which are not independent operators. These are derived from the basic operators actually. So instead of writing using basic operators, lengthy and complex queries, these derived operators are used to reduce the complexity of the query processing action. But whatever the operators which we have in these two categories are not sufficient, and some more additional facilities are required to express our queries in effectively. So that's why these relational algebraic operators are introduced, more operators. Those operators are known as extended relational algebra operators. Select, project, union, set difference, Cartesian product, and rename. These six are basic relational operators because these are defined themselves independently. Such operators are basic relational algebraic operations. And derived or relational algebra operators. That is intersection, natural join, division, and assignment. These are derived. Derived means these four operations are defined by using combination of the basic six operators. By using the basic six operators, combination of these six operators, these derived relational algebra operators are defined. Extended. Extended means additional features are added. So the extended relational algebra operators are generalized projection, outer join, aggregate functions, and data manipulation languages are also included. DML operations, insertion, deletion, updations. These are also included in our relational algebra. Basically, this is a query language, but in the time is going on, then we would like to include our database languages, all three kinds. That is definition, storage, definition, manipulation, and query based. All these four kinds of constructs were introduced or included in our commercial languages. SQL is such language only. Uh, by pronunciation, we may consider it as a structured query language. It seems to be a query language, but this consists of all kinds of constructs. It consists of DDL commands, DML commands, query language commands, as well as storage structures also. So that's why it's being a basis for many commercial query languages. This relational algebra was extended with these additional operations, which consists of some DML structures also. So I'll explain the concepts of these relational operators today one by one. Basic relational operators. First operation is select operation. Select operation is a horizontal partitioning. Horizontal partitioning means from a relation, only some set of tuples are going to be displayed as per our need. As per our need means which satisfies the given constraint. So select operator notation is here sigma of R with predicate P. So sigma of R means here sigma is select operator here. You observe. Here sigma represents our select operator. P represents predicate. Predicate is known as selection predicate. That is a constraint. So whichever the tuples satisfies this constraint, those tuples only will be listed as a result. R is our input. So sigma is our select operator, P is the selection predicate, and R is our input actually. So this select operator is defined as mathematical notation. We are writing first sigma of R with P is equal to set of tuples T such that T belongs to R and P of T. That means here, wherever the predicate P satisfies in the input relation R, all those tuples are going to be listed as set of all tuples. Set of T means T such that. So T belongs to R. From R we are taking and P of T. That means where the predicate is going to be satisfied in the tuple, those tuples are going to be listed actually. Where P is a predicate, we have been telling. What is P here? P is a predicate means it is a formula in propositional calculus. Consists of connectivities and attributes and relational operators. And connectivities. Connectivities means here AND operator, OR operator, NOT operator. And attributes will be there. So how to write this predicate? The syntax of the predicate is attribute, operator, attribute or constant. That means it is a condition, no? We have to write some relational condition first. So what is an operator here means relational operator, because this being a relational constraint, these relational operators must be used. That is equal to, greater than, less than, not equal to, greater than or equal to, less than or equal to. That means we are writing attribute. For example, we are going to write it as a sigma branch name is equal to per each of account. So from the account relation, wherever the branch name is per each, the respective tuples are going to be displayed actually. That means this is a condition we have written in the form of a constraint that is known as a propositional logic formula. One more example we are giving. Let us assume that this is a relation ABCD and having this 4 tuples are there. We are writing the constraint. Please observe down. Sigma A is equal to B and D is greater than 5 of R. So A is equal to B means that content of the attribute value A and attribute value must be equal in a particular tuple, as well as in the same tuple if the D is greater than 5, the respective tuples are displayed. So first condition, first tuple we will take alpha is equal to alpha, right? The first constraint satisfied. AND operator means second constraint also must satisfy, d is greater than 7. So this will be listed. In the second constraint, second tuple, first constraint itself doesn't satisfy. In the third tuple, first constraint satisfies, a is equal to b, that is beta is equal to beta, but d is not greater than 5. So second condition doesn't satisfy, this won't display. But fourth tuple, b is equal to beta is equal to beta and d is also greater than 5, this will be displayed. That means from the four tuples of relation R, the first tuple as well as the fourth tuple satisfies the predicate given, only those are listed. That means we will call it as a horizontal partitioning or a horizontal fragmentation. That is tuples wise we are selecting here. So by using this, most of the queries we are able to write as per our requirement actually. Another example is there. Student data is there here. You observe 6 students data is there. We are writing name is equal to blogs of student. Blogs is only one attribute satisfies. So that only one tuple satisfies the name is equal to blogs. That particular tuple will be get displayed. Second operator is projection. Projection is because selection is horizontal, no? Projection is known as for vertical partitioning or vertical selection. Vertical means attribute wise. So in the previous case, we didn't represent any of the vertical partitioning. So then automatically it displays all attributes. But by using this project operator, we can list out the tuples which we want only. For example, in this relation, I have ABC, 3 attributes are there. I want only true attributes from this relation. So I will use this project operation. This project operator is represented by using a pi. So now you observe here, pi a comma c of R means here, pi means projection. Only attribute A values and attribute B values are displayed. Attribute C values are not displayed. Now you observe, A comma C. So attribute A, attribute B, attribute C. 3 attributes are there. Among them, we want only AC only. So that's why A attribute is displayed, C attribute is displayed, B is going to be not displayed. So as a part of this, AC means we will get alpha 1, beta 1, beta 2. Total 4 tuples are there. But you observe in the result, 2 tuples are repeated, duplicated, redundant. At the time of defining our relational database, I explained to you, a relation consists of unique tuples and unique attributes. Please remember, unique tuples and unique attributes. Because this relational data model is based upon the set theory concept, the duplicates are not going to be included. So that's why this alpha 1 is not going to be included twice. Only once it is going to be included. As a part of that, our output will have only 3 tuples, not 4 tuples. Because one tuple was repeated, that tuple is going to be eliminated actually. So projection operation is as a selection operator is used for vertical fragmentation or vertical partitioning. Horizontal partitioning is by the selection operator. Project operator is used for vertical partitioning or vertical fragmentation. So this is the notation. A general syntax of our projection operation is pi of a1 comma a2 comma etc ak of R. That is, whichever the attributes are there in R, the required attributes can be listed here. It need not be in the same order as in case of relation schema R. It can be any order or in the order in which you would like to get the display. I may write it as a A2, A1 also. I may write it as a CA also. The order can be determined by us in which order we would like to get the display as an output actually. These attributes are the names of the attributes in the relation R. It must be available in R only. The result is defined as the relation of k columns obtained by the erasing the columns that are not in the listed actually. Duplicates are removed from the result since the relations are sets. All of us remember, in case of relational algebra, if any resultant relation consists of duplicate tuples, those are automatically eliminated. Why? Because a relation is a set actually. So that's why we will write whatever the attributes are required for us. We will list out those attributes by using operator by operator. So an example of an account, I want only account number and balance. I want to get the display of each account holder's balance. Then I write pi of account number comma balance of account, where account is a relation. The schema was represented of account was represented in previous sessions. Another example, student is there. I want to know only student tutors only. So pi you observe pi tutor of student. So tutor means how many? 1, 2, 3, 4, 5, 6. So 6 tuples I supposed to get. But remember here, a global repeated twice. So that's why once it is deleted, as well as can repeated twice, that is also eliminated once. So total 6 are there, but 2 of them are repeated again. So those are going to be repetitions are eliminated. So the result relations do not contain any of the duplicate tuples. I am talking about the duplicate tuples. It's not values, duplicate rows. Okay, so that may not be included. Any duplicate rows are there, those are going to be eliminated. The third operator is union operation. Union operation is the same as our set union operator. But in case of this union operation, being a relational algebraic operation, two relations must be, you observe here, select and project. How many input relations we are taking? A single input relation. Those two are known as unary operators. Select and project are known as unary operators, for which only a single operand is an input actually. But coming to this union operation is a set theoretical algebra operators, same as your set operations only, but inputs are two. That means two sets are going to be union, no? Similarly, two relations are going to be applied union operator. So what is this union operator? Before writing this union operators, the two relations, that is two operand relations, must satisfy compatibility condition. What is meant by compatibility condition? The two operand relations must have same number of attributes and same type of attributes, same domains also. That means the set theoretical algebraic operation can be only applied if the two operand relations are having the compatibility satisfaction. That means both relations should have the same set of attributes, the same order, the same domains, possibly with the same name. So let us assume that two relations are there, R and S. You observe R and S. Can I apply union or not? Before checking the applying of union, I supposed to check both of them are compatible or not. So here AB, two attributes are there in the relation R. Similarly, in the S relation also two attributes are there. I can union. Then what is the result of this union operator? First, in case of union operator, both structures are same. So that's why the structure will be the same. That is, the set of attributes are same in the resultant of the union of these two relations. And what about the tuples? First, it will include the tuples of the first relation. Then it will include the tuples of the second relation. Any duplications are there, then automatically removed in case of relational algebra. So this is the notation we will use, R union S. How to define? R union S is a set of tuples T such that T belongs to either R, S. And for R union S is to be valid, Rn must have the compatibility. Compatibility means they should have same arity, same number of attribute. Compatibility means attribute domains must be, respective attribute domains must be the same. And if you have two operand relations are having the same way, then easily you can apply this union operator. For example, CS student, master student. Both you observe student number, name, year. Here also student number, name, year are there. Three attributes are, number is 3 in both cases, and compatibility is also holds good. Then I may do this union operator if necessary between these two relations. So CS student, union, master student. First I list out all CS students are included, S1, S2, S3, S4. So S1, S3, S4 are included, but while including these master students, S1 eager 5 already there, it won't include. S2 is not there, that will be included. S3 Rosie 4, this is also there, this won't be included. So totally actually the first relation consists of 3 tuples, second relation consists of 3 tuples. So we are supposed to get respectively 6 tuples actually in our union. But 2 of the tuples are repeated, that is S1 tuple as well as the S3 tuple are repeated. So those are identical tuples or duplicate tuples are eliminated. No duplicates. Right? Relations are sets. So that's why no duplicates. That's why duplicates are going to be eliminated automatically. So the result will be S1, S2, S3, S4 only. Even though S1, S3 are duplicated, those are not included twice. Okay, now the next operator is set difference. Set difference means, as in case of sets similar to that only, the tuples which are exist in the R relation and the tuples which are doesn't exist in our S relation are resulted. R minus S means which are in R, which are not in S. For this operation also, the two relations must be having same arity and also compatibility. These two conditions must be satisfied. Now you observe as an example, AB. Two attributes are there, compatibility is also there. So that's why the same structure will be resulted as a AB. What are the tuples? Alpha 1 is there in AB? No, it is not there. Then you can write. Because R minus S, no. So the tuples which are belongs to R but which does not belongs to S, those are going to be displayed. So that's why R belongs to, a tuple belongs to R, tuple does not belongs to S, must be listed. Alpha 1 is there which belongs to R but which is not in our S. Alpha 2 is there which is also alpha 2 which cannot be included in my resultant. Beta 1 is there but beta 1 is not there in our case, so that's why beta 1 is included. That's all. The relations are tuples of the relation R are exhausted, we will stop. So these two tuples are there, that is alpha 1 and beta 1 in R relation which are not in S. Similarly, you can perform S minus R also. Right? So because the difference is not commutative. So that's why R minus S is need not be equal to S minus R. So this is the general notation we will follow for set difference R minus S, and which is defined as mathematically R minus S is set of the tuples T such that T belongs to R and T does not belongs to S, and operator. Please remember that. So to do this, set difference must be taken between compatible relations, that is both of them should have same arity and the respective domains must be the compatible among themselves. One more example, we are taking same examples, CS student and master student. So when you are making as a minus means here, S1 is there, S1 he get 5. This is also there here, which is not included in the result. S3 is there, row C4. S3 row C4 is there, so which is not included. And S4 is there here, but in master student S4 is not there. Only that will be included. Right? So this is a CS student minus master student. So if you are doing reversely, master student minus CS student means we will get only S2 because S1, S3 are there in there. S2 is there in master student, which is not there in our CS student actually. So this is the another operator, fourth operator, which is a set related operator also. The next operator in basic relational algebra operations are Cartesian product. Cartesian product means we have to map each tuple of the first relation with each tuple of the other relation. That combination of the mappings must be listed out. That means here the output consists of all attributes of the first relation followed by all attributes of the second relation, and map each of tuple of the first relation with each of the second relation tuples, then listed the result. Because of this, if the first relation consists of n tuples, if the second relation consists of m tuples, then the product consists of, Cartesian product consists of n by m tuples. So that's why you observe in this example, the first relation R is having AB, two tuples are there, alpha 1 and beta 2. And the S relation is having three attributes, C, D, E, and with 4 attributes. Totally, how many attributes are there here? 2. There 4. So 2 into 4 means 8. So the Cartesian product of R cross S, we will represent with the cross, and will consist of 8 tuples. And what are the attributes? Attributes of the first relation followed by the attributes of the second relation. Now you observe here alpha 1. Alpha 1 will be mapping with the first attribute, second tuple, third tuple, and fourth tuple also. That means I'll get alpha 1, alpha 10A, alpha 1, beta 10A, alpha 1, beta 10, 20B, alpha 1, gamma 10B. Similarly, second tuple will also map with the all tuples of the second relation. So the display of the Cartesian product is as shown below. R cross S consists of all attributes of the first relation followed by all attributes of second relation, A, B, C, D, E, and mapping of the each tuple with the each tuple of the another relation. So it will be represented mathematically R cross S, and it is defined as like this. How to define R cross S? It consists of the tuples in the form of TQ, where T belongs to R and Q belongs to S. And the structure of our R cross S is structure of the relation R plus structure of the relation S, that is concatenation. Assume that the attributes of relation R and attributes of relation S are disjoint, then R intersection S is pi, then attributes names can be specified as it is. If they are not disjoint, then the remaining must be used by us properly. Sometimes we may use qualification also to access the data of the common attribute names also. That means qualification means, for example, an attribute to A is there in R relation as well as in S also. I may represent them as R dot A and I may represent it as R dot B. R dot A means S dot A. So R dot A means it will be having, for example, R dot A will be represented similarly S dot A. R dot A means the attribute A in the R relation, S dot A means the attribute A in the S relation. Like that we can treat them as a different way by using the qualifying concept actually. So another example of student course, you observe student is having 3 tuples, course is having 3 tuples. So 3 into 3 means 9 tuples I will get as a Cartesian product of student and course. You observe S1 Jones is mapping with CS250 programming Sun. Same S1 Jones is mapping with CS150, programming Sun. S1 Jones is mapping with CS390, subject is specification, specs and equipment is Sun. So totally 3. Similarly for second tuple, similarly for third tuple of the relation student actually. Now you observe attributes are total 5 and tuples are 9 actually. So another example is there, student and staff. You observe 1, 2, 3, 4, 5, 6 students are there. Staff is 1, 2, 3, 4, 5, 6, 7, 8, 9 are there. So 6 into 9 means you will get approximately 56 tuples. So 56 tuples will be there, and those tuples are going to be having attributes of the student followed by attributes of the staff. So you observe here, this is one kind of such type of representation having many tuples actually. So these are all the 5 operators we discussed. One more is known as renaming operation is there, that is used to represent some result of a given operations with a new name actually, or result of a relation with another name. These operations are going to be individually, it may not be that much useful to us, but when they are going to be combined to construct a complex expressions by using all these kind of operations, may fulfill our requirements of accessing data as per our needs actually. So here we can write combination. For example, I want to get all tuples from R cross S where A is equal to C. That is, the attribute A is equal to having the same value as attribute C. Then from R cross S, I will get the result of only 3 tuples. Total 9 tuples are there. So we want to check A equal to C. A equal to C means alpha equal to alpha first one. Okay, alpha is equal to beta is equal to beta second one, and beta is equal to beta third one. So these 3 tuples are here listed, which satisfies the condition A is equal to C. That is, what are the operators we are using? We are using the operators of the selection as well as the Cartesian product. Like that, we can use a combination or composition of these operations as per the needs of accessing the data, as per the requirement of implementation of logic also. Like that, we can combine them actually. The last operator is rename operation. Rename operation means we would like to give a new name to the result or intermediate results of a relational algebraic expressions. We can use this operator. This operator is used to represent notation wise is a row. Row is used to rename. That is, we can refer the same relation with another name also, not only its own name. Whenever we are giving a rename with that name also, I can refer it. For example, here row of x of e, that is e is hereafter the relation e is also used as a renamed as a x. I may use e or I may use x also further. Need not be the entire relation. Only part of the relation can also be renamed. For example, another one, row x of a1, a2, etc., an of e. Only those attributes are going to be connected, combinedly known as a sub-relation. No, that relation is going to be renamed with x also. So that's why renaming is generally used when a set of complex queries are written by us, and we will use this rename so that it can be accessed. The queries are going to be written more efficiently. Right? So the combination, selection projection, selection horizontal decomposition, vertical decomposition, and this combination can also be used by us as per our need actually. Right? So these are the basic operators of the relational algebra. Various queries of this relational algebra are going to be discussed further by us, and more queries are returned by using the set of these operations. So next session, we'll discuss about the various types of queries able to write in relational algebra as per our requirement by using these 6 operators and how to represent them more effectively in relational algebra. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.